Hello guys, this is Yusuf and today I will be introducing a new paradigm for self-supervised learning. But first, let's look at the shortcomings of the methods and approaches that we've talked about so far. So for contrastive methods, we have mentioned how the network learns good representations or high level semantic features by comparing two different views and trying to see how these features prevail through the different views. So you try to create two different samples out of the same image, rotate one image and try to learn that the nose is still present in both image and this is still the same object. However, this introduces some major drawbacks that limit the use of contrastive learning or these methods in different domains. The biggest problem is that we have the augmentations that really control the quality of what we're learning and how we're learning. So first, the augmentations might introduce certain biases. For example, if you do too much color-based augmentations, the model might be biased to ignore color because it's not really an important feature, right? Like when you compare two images, regardless of their color, they're supposed to always be the same, so maybe the color is not really an important feature. And these biases might be limiting when you want to take this model and apply it on a different data set or um, for transfer learning tasks. This might be limiting because this might not be the case, and color might be, for example, an important feature to be used for a certain data set. So this is something to keep in mind because the augmentations are introducing certain hidden biases into the model, and they also control the quality of the learned representations. And we've seen how the representations, for example, for VicReg or for Buell were very much dependent on like how the pipeline. I think in the Buell paper you also find like a graph that talks about how using different combinations of the augmentations result in different levels of performance. Sometimes using very light augmentations does not result in like good performance. Sometimes this augmentation is better than this augmentation. So it is also a very heuristical approach, and it could be limiting to the representations we're learning. And finally, this approach of defining augmentations of different views is very easy to do for images. We know how to preserve these different views through different augmentations, but we don't really have this for different data modalities, and this makes it hard to use these contrastive approaches in different domains. If you were to go for audio, for text, for tabular data, it becomes somewhat harder to define good augmentations and what are like good augmentations for text. This is like a very it's not as usually as good as images. Same for tabular data. So this is one thing to keep in mind because it's like a very limiting and restricting to these methods. On the other side of things, the predictive methods that like math autoencoder that we have talked about um, rely on reconstructing part of or denoising part of the input. So they don't essentially require you introducing a certain inductive bias or a certain or relying on augmentations, which is good. They can be applied to different data modalities and to more domains. However, these methods typically learn less meaningful features and are weaker than the other contrastive methods. They don't learn as good as features because the model still has to focus on reconstructing the pixels and the low-level features, which may not be very useful for a prediction, like whether this pixel is a bright green or a less bright green. It doesn't really matter. And the performance is, as we said, it's limited compared to the other methods. And because of this like focus on the low-level features, these methods, although they're really easy to generalize or easier to generalize to other data modalities, they're still very restricted, not as good, or there is an area of improvement here. So if if you were to look at at this image, and this is to motivate how we as humans, we don't really operate on the pixel level. We don't really operate on this very low level features. We usually have higher semantic features and higher semantic understanding that you, if you were to look at this image, for example, and you try to predict where exactly will the ball be in a couple of frames, well, you could probably think that, yeah, well, the ball is going to go into the goal, but where exactly? Can you tell me the exact pixel colors? Well, this is like something that we would probably not be able to do. And as a matter of fact, in this exact frame, the ball goes over the post. So if you were to reconstruct how accurately these pixels will what values they will take, you will not be able to. But if you have like a good understanding of what's going on, if you're maybe a football fan, or you know the players, etc., you might have a good idea where the ball will be. So the ball will be inside of the net, the ball will be outside of the net, and so on. So yeah, this is exactly what we have just mentioned. The values might be anything in the color range, and you would not be able to reconstruct it. But high level, highly semantic features, like understanding of the game of football, would allow you to tell, yeah, the ball will be inside of the net or outside of the net. And this is where we now come to this idea that we want to do predictive, but we don't really want to do predictive on low level features or on pixels. We don't want to be predicting the pixel values. We want to be predicting something more sophisticated, something more meaningful. And we'll see how we go from from the contrastive or the joint embedding architectures, where you have two networks or two encoders. One takes an input, one takes a different input, and then you have some loss or some method of comparing how these two outputs of the two networks fare well together and how they're similar. And inside, for example, for BL, inside of the X encoder, you'd have like the normal network, you'd have the predictor and the projector. So like these are just blocks of encoder. In the end, you're usually comparing two embeddings, and this is why these are called joint embedding architectures. For generative architectures, like we talked about masked encoder in previous lectures, the masked autoencoder takes an input, and this input is usually noised, and then produces some latent representation Z that is used to decode this input. And then you compare the original input Y, so this is like the uncorrupted input, with the output of the decoder, the reconstruction, and you compare these. Now, we're going in this lecture, we want to do something similar, but we don't really want to do this on the pixel level. Notice that when we're comparing the loss function of the generative architecture or these predictive architectures, we are taking the raw input Y, and we are comparing it to Y hat that is coming out of the decoder, and this is like just image pixel values or tokens. However, we want to do this on a higher semantic level, and this is why, and this is where the joint embedding predictive architectures come from, or JEPA. The idea is simply, okay, we don't want to be doing this on the low-level semantic features. Let's do our comparison of the data on and the different parts of the outputs. Let's do this on in the abstract representation space, in the feature space of the network. So this sort of combines both generative architectures and joint embedding architectures. You can think of this as like a hybrid combination of masked autoencoder and BIOL. So you have an input X. This could be like a corrupted input. You feed it into the encoder, and then you have some representations that predicts some latent space representation. So now this is S of Y, this is not Y. So your predictor is not outputting the raw pixel values, but it is trying to predict some representations. And these representations that we want to predict are the ones that are coming from another encoder Y. So the Y encoder encodes maybe the uncorrupted version of these features, and we're now doing the comparison in the embedding space, not in the pixel space. So to motivate also to try to get like an understanding of all of these like different networks and how they're working, let's take a minute and talk about the game of charades or Pictionary if you've ever played one. If you haven't played one, then the rules are very simple for these games. You usually have some one player, so you play this with friends. You have one player who's giving a certain message or topic to convey to their teammates. And this could be a movie, for example. So you get a movie name, and you need to tell your friend what this movie is without actually telling them the name. So what you do is you try to pick highly semantic features of that movie, something that is very memorable. Like this is a movie that talks about an American nuclear physicist in World War II, and maybe you draw like a bomb, a nuclear bomb, but like an American flag and like a scientist on a whiteboard, and then you try to find the features of this movie, the relevant information that would tell someone that this is the movie I am talking about. And then your friend would take this context that you provide, and they would try to predict what exactly is this message, what is this movie you're talking about. And if they've seen the movie or they know the movie, they'll be like, yeah, this is the movie Oppenheimer, for example. And the more typically for these games, the more you play with your friends, the more you know what would really make them understand your message. So you typically get better at the game by playing with friends that you really know well, and you sort of know what features to pick that will make them like know like just in a second like what movie this is. And this is similar to this scene from Friends with Bye Bye Birdie, if you've seen it. So I-JEPA, or JEPA for images, is very similar to this sort of charades game. So what we have is we have a network, a context encoder, that will take only certain sequences of the image. So we're working with vision transformers. We have patches, non-overlapping patches of the images, and the context is just going to get a certain set of these patches. So not all of the patches, we sample a set of the patches, and it's going to produce representations for each patch, trying to encode what information is included inside of that patch. And this representation will be given to a predictor. And what will the predictor be trying to do? Well, there are missing parts of this image, so the predictor is going to try to predict these parts of the image. So you take one, for example, part in the blue, like the four patches next to at the corner, at the top left corner, and these are like the ones we predict. So before we give them to the predictor, we put some mask tokens there to tell the model, okay, you have these representations that are coming out of the context encoder. We want to predict these four top left corner patches, and we put the mask tokens there, and we give this to the predictor, and the predictor is going to produce representations for the blue corner. And then for the target encoder, we're going to sample the patches as well that represent the top left corner, and we're going to feed this. So this is the blue part, and we try to compare if the predictor can output similar representations for these patches to the target encoder. And then we can do this for different patches. So we select another subset, like the red patches. We still have the same context for all of these patches, but we sample different target or different representations that we want to learn. So we ask the question based on the information that you see from the context, what would be the representations for these other parts that the context has not seen or does not include. And we'll get into the details of how the architecture works, but this is just a top level view of how this network is operating. This is the context that, like the game of charades, you're trying to pick information or you're trying to encode the information of the message as semantically rich as possible, and you pass this to the predictor, and then the predictor takes your representations and try to make the prediction. Okay, given this information that I see from the context, what is the message, or what is the message of this region I'm trying to predict? And we're operating in the representation space. So when we compare the output of the predictor to the output of the target encoder, we are comparing representations. We're not comparing pixel values. So this is how you would typically have a training run. You would sample some patches from the image. You would make sure that the patches you sample for the context are non-overlapping with any of your targets. So you feed the context patches into the context vision transformer or the context encoder, and then you get the representations for each of the patches. You get the representations for, this is the 7th, the 8th, the 10th, the 11th, the 14th, and the 15th patch. And these are the only context patches that, or the representations that the context or the predictor will be using. And then if you want to make a prediction for the top left corner, you would add to these representations some mask tokens in these regions, so that the predictors knows what places it is trying to fill in. And then the predictor will output the representations for each of these patches. Now, on the other side, on the other branch of this joint embedding architecture, you select the same target. So you typically select the target first, and this is how you insert the mask tokens in the upward stream. So you select the top left set of patches. This is the ones you want to predict, and the target is going to produce representations for all of the patches. You will select these top left patches, and you will try to compare if the predictor managed to get the same representations that are coming out from the target vision transformer. And we typically compare the representations with an L2 loss, and for the paper this was completely fine. The context encoder tries to encode relevant context for the predictor, so it's trying to search for the information, the semantically rich information, and tries to encode that. And usually the context encoder is the module that you have self-supervised, that you take out of the self-supervised pre-training. This is the module that you're going to use in prediction. So this is typically the network that you use afterwards. And the patches are usually sampled in a non-overlapping manner with all of the target patches. So you try to avoid having this trivial prediction where you've encoded something that you're going to try to predict, because this we know that this results in collapse. So we try to have non-overlapping patches with the target encoder. However, it's also sampled independently from the target patches. For the predictor or the predictor encoder, we use the context that is coming out of the context encoder. We insert the mask tokens in regions where we want to make a prediction, and they usually contain like the positional embedding information as well. and then we iterate over each set of targets. So you can think of the target set as sort of a label that you're trying to predict. And for each target set, we feed this into the predictor. We get like some representations out, and we compare them with the target network representations if they're how they're similar. And we do this for all of our target sets. So this gives us sort of a freedom to like sample different targets from the same image and try to predict, okay, if it has a tail, would it have ears? If it has a tail, would it have like claws, or would it have wheels? And based on the information from the context, you're trying to predict different regions, and each region is sort of like a training iteration. And all the predictions being done by the predictor are in the representation space, so we don't have any encoder, any decoder, or any architecture projecting this back to the pixel space. And we are comparing or making prediction or producing representations in the abstract representation space, in the hidden space of the network. And finally, the target encoder, which is giving us the labels. Where does this come from? This is the network that is telling us what representations we need to output or trying to match, and where the semantically rich information is that we're trying to learn. And this network is typically, and you've seen this trick before in BL, this is an exponentially moving average of the context encoder, which is supposed to be the teacher or the wiser network that has the semantically rich information. And this is very similar to BL, so you can probably now see how this is sort of a mixture of BL and the mouse autoencoder. Here's some examples for how the images would look like in different during training. So you have the images on the original images. You sample certain context, and the context is usually bigger than the targets that we have. And then you sample a set of targets that we're going to try to predict. And these targets sort of each represent some feature that we're trying to learn, and then we're trying to maximize the amount of information that we're learning from the image. We're trying to look at, okay, it has ears, or it has like a body. Does it have like a nose? Does it have a neck? Does it have a leg? And each target is sort of like independent from the other targets, so you get a loss from each of the targets, and you backpropagate the loss. So it's sort of making the representations or you're learning from the data a lot more rich. So let's look at some results of these networks. So we'll find that I-JEPA is, and I believe it might still be the current state of the art in self-supervised learning. When you look at like linear evaluation, when you just freeze the context encoder and just fit like a linear layer to predict the classes on top, I-JEPA approaches 80% on like the smaller model, and breaks the 80%, which is like a huge feat for a self-supervised model with the larger models. And it has like a very interesting scaling where if you make it bigger, it learns more semantically features. If you make the images like have a higher resolution, it will also learn like better features. And because we're always like having, for example, targets that are much smaller, and where the context is also part of the image, we require much less GPU compute resources than to train, because we're only using partial parts of the image. We're not feeding the entire image or producing representations for the entire image. And we also don't have a decoder. We're not trying to project this back to the embedding space. So we're operating in the we're not trying to project this to the pixel space. We're just trying to do the compare the encoders in the representation space, and this scales much better and is faster to train and faster to reach these performances than other architectures. And with only 1% of ImageNet data, so if you were to only sample 1% of the images in ImageNet, I-JEPA can still reach a 77.3 top 1 accuracy on ImageNet, which is quite impressive, especially if you compare it to other methods that are not using data augmentation. It is sort of in a league of its own. And if you look at other methods like Buell and SimClear, you'll find that there is like a very strong improvement over these methods, which should have like more richer semantic representations. And if we look at different data sets, we'll also find that the performance gains that we get from I-JEPA is still much better than the other non-data augmentation methods. On some data sets, it's weaker than I-BOT. I'm not sure if we will talk about I-BOT, but I-BOT also uses like extra view augmentations. However, on certain data sets, their performance is still very close, and this is without using any data augmentation, so which is really impressive. So in summary, I-JEPA combines the techniques of predictive and joint embedding approaches. It merges these two paradigms together and sort of gives us a very nice combination of Buell and masked autoencoder. I-JEPA does not really rely on augmentations or different views of the images, so this allows us to learn high semantic features because we're doing the comparison or the learning or the reconstruction on the representation space. However, we're still not relying on augmentation, so this is a flexible approach that could be applied to different data modalities and still produces really good results, which is something really interesting. And it would be interesting to see like this JEPA approach in the future as well. So yeah, this is it for I-JEPA. Thank you for listening.